thanks for tuning into this Revision Zone Maths video. In this video, we're going to be trying to get a better understanding for calculating derivatives of non-trivial functions. Just so we are all on the same page, it's good to take stock of what we've seen so far so we sort of know what's new and how the theory develops. So far, obviously we've seen the definition of differentiation, that's where it all started, but the definition of differentiation is not good enough in terms of using it every time to calculate derivatives from scratch. So we usually use higher order rules to be able to differentiate things. And so far what we have is we have two higher order rules that were actually already proven. These were proved much earlier on in the video series on differentiation. So the first rule basically says if I have a function made up of adding two separate functions, then to differentiate the function, the more complicated function, I basically differentiate each one of the less complicated functions and add them up. Okay, so that would give me the derivative of the more complicated function. The second rule we've seen is if a function capital F is obtained by taking a function lowercase f and multiplying by a, then the derivative of the function capital F can be obtained by basically just taking the derivative of the function lowercase f and multiplying by a, where a of course is any real number. Now, we've not seen Rule 3 so far, but the point is Rule 3 is just a direct application of Rule 1 and Rule 2. So when we combine Rules 1 and 2 together, we can write something of the form, which is Rule 3, which is if you have a complicated function capital F made by taking two functions lowercase f and lowercase g and multiplying them by alpha and beta respectively and then adding them up, then the derivative of capital F is just going to be the derivative of lowercase f and lowercase g multiplied by alpha and beta respectively, and then just summed. So these, what I've said so far, these are basically higher order rules. And in this video, we're going to be looking to work out rules which are analogous to these sort of rules, but for more complicated combinations of how functions are being combined. Other than that, we've also seen some sort of simpler rules where we've gone away and differentiated a function of a particular type. So a very important example is obviously the derivative of a generic polynomial. We've seen that. And the other example is the derivative of an exponential. We've also seen that. So what are we going to do today? Let me make a note of it, and then we can go into detail and actually do it. So we're going to look at different rules. The rules we're going to look at for differentiation, there's a rule called the product rule. So we're going to look at the product rule. We're also going to look at another rule called the quotient rule. Quotient rule, if I can write this. And lastly, we're going to look at something called the chain rule. So the chain rule. We are going to try and derive them. So let's jump in and try to take a look at each one of these rules in turn. Let's have a think about what the product rule actually says. The product rule says if you've got a function capital F of x made by taking two functions, say a lowercase f of x and a lowercase g of x, and multiplying them, then to differentiate capital F of x, namely to get capital F prime, what you do is you differentiate the lowercase f and you multiply by g, and you differentiate the lowercase g and you multiply by f, and then you add up your results. Okay, so let's see why this might be true. So of course I'm just going to say proof, and we're going to go to the definition of a derivative. So we want to differentiate capital F. So the definition tells me that I take capital F and I evaluate it at two nearby points, x plus h and x, and I subtract them, and I divide the change in y by the change in x and take the limit as h tends to 0. But we know what our capital F actually is. Our capital F is fg, so I'm just going to put fg in and then see how this comes out. So it's still divided by h, and the limit is there for now. Now at this stage, most people would come and think, okay, there's no way, there's nothing we can do here, because somehow we have to go from this statement to be able to manipulating and getting limits that we can evaluate and re-express as derivatives in some way. However, the creativity of mathematicians is quite impressive. So what a mathematician would do, a mathematician would say, okay, well let me just rewrite what I have there, And let me do that first. F of x, g of x. And let me make the numerator slightly like this. Good. So the mathematician would say, ultimately, adding 0 to something, to some number, to some function, is not going to change that number or that function. So let me just add a 0 here, right? And this is an ingenious step, really. But what they then go on and say, hang on, we could actually re-express that 0 as a quantity added and the same quantity taken away. So let me recopy everything here. X plus h minus f of x, g of x, and then I'm going to do the fraction line first and re-express the 0 as follows. So suppose I actually add f of x and g of x plus h. And then I better take away the exact same thing because I want this thing in the brackets to be 0, so I've got to take away the exact same thing. F of x, g of x plus h. Okay? So now, so our 0 here, as I've said repeatedly, is basically this thing here, which makes perfect sense. Okay? So now let's just reorganize what the numerator says. This shouldn't be too hard. What I'm going to do is I'm going to cheekily take this term here, and I see that there's an f here, and there's also, there's a g evaluated at x plus h here, and there's a g evaluated at x plus h here, right? So I'm gonna put those together. So let's do that. X plus h, g of x plus h minus f of x, g of x plus h. And of course that then means I'm left with two other terms, and I'm going to write them by writing the positive first because it just looks nicer. So f of x, g of x plus h minus f of x, g of x. And of course the whole thing here is over h. That's a mighty long line. So at this stage, again, it might look like we're not making any progress, but we actually have made progress. We can actually look at this more carefully, and we can say, well, I can factorize g of x plus h from the first two terms, and I can factorize f of x from the last two terms. So let's do that. So I've got limit as h tends to 0, f of x plus h, take away f of x, and here comes the factorization. I've got the g of x plus h plus, and here comes the second factorization, f of x, and then I've got g of x plus h, take away g of x. And now I've got to have h for the entire fraction here, for the entire term here. But of course, I can use some rudimentary algebra and split this up by actually having my h go here and my h go here. And now you start to see this looks so much nicer because ultimately what's going to happen is the limit is of course going to apply to every single thing in this big bracket because the limit initially applied to every single thing in the big brackets there, right? And that's exactly what we have. So everything that was in this big bracket at the beginning is actually also in the big brackets at the end. Okay, so let's perhaps make a bit more room and continue with this. So at this stage, what we can do is we can basically take the limit to the inside. So the limit goes in and it's going to apply to the f of x plus h minus f of x over h. And also, it's also actually in this case going to impact the g of x plus h because there's a h in the g. But then I have the limit applying to the second term, which is going to be f of x. Of course, is not going to play a part in f of x, but it's just there for now. And I'm just writing it out so there's no confusion. So we have that over h. Now at this stage we've got to start to evaluate the limit. So let me put some more brackets in just so there's no confusion as to what the limit's going to be applying to. So I've expanded the first limit to be able to say this. So once we have this, we can actually say the limit is going to, this first limit is going to apply to both that term and it's going to apply to that term because both of those are in terms of h. But the second limit is only going to apply to this thing here because the function at the front is purely in terms of x. So that's not going to really play a part in the limit. So if I write that down, I'm going to say the limit as h tends to 0 of f of x plus h minus f of x over h multiplied by the limit as h tends to 0 of g of x plus h. Now, the reason why this multiplication is there, of course, because there's a multiplication there, which we don't normally write down, but I've written it explicitly because limits are involved. And then we've got the plus, and the f of x is going to come out of this second limit, as I've already said. So I'm going to have the f of x come out, and then I'm going to have the limit, which I will write down explicitly just to make sure there's no confusion. So we've got that. So we've got the limit as h tends to 0 of g of x plus h, take away g of x, and the whole thing is over h, and let's just put some brackets in here. So now at this stage, we should notice actually this thing here is just a definition of a derivative, and this thing here is also just a definition of a derivative. So I can rewrite this as follows. So this is going to be f prime, because the function being differentiated first is the function f. I'm just going to write the limit as g x plus h of gx plus h as h tends to 0 for now. And then the remaining term is going to be f of x times by g prime x, which is obviously, as I've said, that term there. So this is looking very promising. The only thing we have to think about is this. Well, what happens to g as h tends to 0, where the argument of g is x plus h? Well, as h tends to 0, then x plus h is just going to get closer and closer to x, because h is going to go to 0. Okay, so what I can actually say is this gives me the same thing as f prime x, g of x, because as I've said, the x plus h goes to just x as h goes to 0. Then we've got f of x times by g prime x. And this is precisely what we wanted to show. This is exactly what the product rule is. It is worth making a remark here actually, because differentiation has two sets of notations at least, the Newtonian notation and the Leibniz notation. It is worth seeing what the product rule would look like in Leibniz notation. And we can easily go from Newton's notation to Leibniz notation by just defining certain things. So if I define my function f of x to be the variable u, and my function g of x to be the variable v, then if my function capital F is defined as y, then using the definition of capital F, I can arrive at the definition of y in terms of u and v. So u and v are functions here of x. Okay, so y is a function of x, and so is u and so is v. And the way we get y is by multiplying u and v. So once we have that, what if we want to differentiate y with respect to x, right? The product rule would be used in this case, and of course all I've done is I've basically said, well, if I have u as a function of f, then when I differentiate f with respect to x, then that's the same thing as du by dx. And similarly, if I have v as a function of x and I define that to be g of x, then when I differentiate g with respect to x, that's the same thing as dv by dx in sort of Leibniz notation. So once I have these statements, I can go and put them into this form. Okay, so if I replace my f prime by du dx, my g prime by dv dx, my g by v, and my f by u, I arrive at this statement here. So my dy by dx is du by dx times by v plus u times by dv by dx. It's just another way of stating the product rule. So I'm just going to put that in a box because it's so important. So we're going to put a red box around it. Okay, and obviously we have already proven this. I'll just put a box around that. Both the statements are exactly the same. So we can now move on. So we've just seen something quite sort of abstract and general. It's worth to sort of see an example to actually get a feeling for how this works out in practice. So here we have a function f of x, which is x squared times by x cubed. Obviously, before we would have just combined the powers, but in this case, let's use the product rule. So let us define f of x to be x squared and g of x to be x cubed. So g of x is x cubed. So once we have that, I know that the product rule tells me that f prime of x is going to be f prime x g of x plus f of x times by g prime x. Of course, I should say in this case, what that then tells us, I should have said that earlier actually, we've defined f and g in that case because our capital F of x can now be re-expressed as lowercase f of x times by lowercase g of x. So we see we get back to the statement we actually started with by making these definitions for f and g. So coming back to the actual statement here, let's now use this to work out the derivative. So I know that the derivative here is going to be, well, how do we differentiate x squared? Well, that's just 2x. That's just a standard derivative. And then I'm going to multiply by my function g of x, which is x cubed. So I'm going to write that down. And then plus, how do we differentiate g of x? Well, that's just going to be the derivative of x cubed, which is going to be 3x squared, but I've got to multiply that by the function f of x because I've got an f of x there, and that's just x squared. So I'm just going to put x squared out at the front here, and then I'm going to multiply them. So now it's just a matter of simplifying this. Well, okay, so 2x times by x cubed is going to give me 2x to the 4, and x squared times by 3x squared is going to give me 3x to the 4. So when I now simplify this, I add the coefficients, I get 5x to the 4. And it is worth noting here that actually if I came to this statement here and say differentiate star directly. So let's do that. Well, how would we have done this? We would have just said f of x is equal to, you use rules of indices to add the powers to get x to the 5. And then we know we differentiate that directly to get 5x to the 4. And here's the magic. The point being that we've actually got the exact same answer in both those cases. So the product rule certainly works. Let's look at another example. So in this case, we're going to work through this in Leibniz notation. So I want my function defined appropriately. So let's define u to be x and v to be x squared plus x, right? So that tells me that my y is actually uv. And that's the form we want y in to be able to use Leibniz rule. To be able to use the product rule in Leibniz notation. And we know in Leibniz notation it's going to be du dx times by v plus u times by dv dx. Okay, so let's try and write this down. So u is x, so du dx is just 1. So I can just write that down. And then I'm going to multiply that by v, and I know what v is because the v is just here. So I'm just going to say x squared plus x. Then we have a plus, and then I've got to write the u down. So the u is just there. So the u is just x. So I write that down. And finally, I write down the derivative of v, but v is x squared plus x. So when I differentiate that, I get 2x plus 1. So once we have that, we can necessarily simplify this. So the 1 is not going to make a difference here, and then I'm going to expand this out and collect terms. So I'm going to get 2x squared plus x, but then when I collect terms, I get 3x squared plus 2x. Now let's come back. Let's come back to the statement we've got here. I'm going to call this statement double star because I called the previous one star. And let's differentiate double star directly. Well, how would we differentiate double star directly? So what's y going to be? I'm going to have to express it as sort of something like a standard polynomial. Well, when you expand the brackets of double star, you get x cubed plus x squared. And of course, we can differentiate each term here. This is very standard. This is the sort of thing we've been seeing. And we get 3x squared by differentiating the first term. We get 3x squared, if I can only keep control of my pen. We get 3x squared plus the x squared gives me 2x. So again, we see by magic that we get the exact same answer. So the product rule works. I hope this example has been useful, helpful in at least being able to see how to apply the product. We will see lots and lots of more examples in future videos. So the statement of the quotient rule says, if you've got a function capital F, and you've arrived at that function by taking two functions, say a lowercase f and a lowercase g, and dividing them this time. So that's how you get your capital F. Of course, when you do that division, you've got to make sure that the thing you're dividing by cannot be 0. So g of x can't be 0 as a function, or you can't take values of x for which g of x gives you 0. So anyway, with that technicality out the way, so once you've got your function f, what if you want to differentiate that capital F? How do you do it? This is obviously not quite a product in the conventional sense. This is what's called a quotient. And here's the rule. The rule looks quite sort of messy at first, but this is one of these things where after you use it a few times, then you sort of get totally used to it. I'm not going to bother with reading out each part of that term. I'm just going to jump into actually showing that this is going to work out. So let's look at a proof, and again, because we want to differentiate this, we go back to the definition. So f prime x, the definition is going to be as h tends to 0, f evaluated at x plus h, take away f evaluated at x, and then the whole thing is divided by h. And of course, there should be big brackets here. We'll come back to those. I'm going to substitute in what my capital F is. Well, my capital F is lowercase f over lowercase g, but the first one is evaluated at x plus h, so that's what I have. And then the second capital F is evaluated at just x, so that's what I'll have. So we actually end up with a fraction which looks like that, which is quite messy. I'm not going to put the brackets in for now. We can put the brackets in later. It's just going to make the screen quite messy. So what I actually need to do is I've got to somehow find a way of being able to simplify this. So what I'm going to need to do is I'm going to have to ultimately come to this expression here and simplify it. And the way to do that is to take that and to cross multiply top and bottom, and to take then that and cross multiply top and bottom. That way I'll get a common denominator. So I'm going to get something like f of x plus h times by g of x. Take away, let's do a little arrow here so we know we're going to be writing up. Take away f of x times by g of x plus h. So that's now the numerator, and I'm going to have a common denominator. Let me first tidy that up a little bit. I'm going to have a common denominator. So the common denominator now is going to be g of x plus h times by g of x, right? And obviously all of that is now the bottom part of this. And perhaps if I'm being very careful, I shouldn't just write the limit above there. I should actually write the limit, so the limit applies to the whole thing. So it's got to be more in line with this sort of place here. So the limit, if I can only control my pen, so the limit as h tends to 0 is here. So we've got that. We can tidy that up further, right? So when we've got, algebraically speaking, we know that if we've got something of the form a over b all over c, that's the same thing as a over bc. So once we have that, I can use that to be able to simplify the triple fraction I have in some sense. So I can basically say it's going to be f of x plus h times by g of x, and obviously take away f of x times by g of x plus h, and then using the algebraic statement, I just say h times by g of x plus h times by g of x. So here we go. So we've now got something which is just a fraction. However, this is still not good enough for me to be able to take the limit inside and do stuff with it and say something meaningful. So we're going to have to turn to a bit of ingenious sort of thinking again, and mathematicians would again just go and add a 0 on the in the numerator, and I'll do that all in sort of one step now, because we've seen that sort of an argument before. So let me rewrite down what the denominator is going to be, which is going to be h g of x plus h g of x, and of course the numerator is going to be, I'm going to start with f of x plus h g of x, and here comes the slightly clever part. I'm going to insert a term minus f of x g of x, and then I'm going to add the exact same term, f of x g of x. So what I've done so far is that thing there is perfectly going to cancel with that thing there, so that's totally 0. So I've not really added anything in terms of the value overall. And then obviously from my previous numerator, that term still needs to be written out, so I'll write that out. So minus f of x g of x plus h. So perhaps I'll take a moment just to tidy this. So this looks much more promising. Now let's start to collect terms so that we can eventually put the limit in and start to work things out. So I see that there's a g here and there's a g here, so I can factorize a g from the first two terms. And I see that there's an f there and there's an f there, so I can factorize an f from the second two terms. So let's do that. So I've got f of x plus h minus f of x, and then here comes the factorization. I've taken the g out, right? And in the second case, I'm going to take the f out first, and then I'm going to put the other things in the factor. So I've got g of x take away g of x plus h. So I've got that, and of course this entire thing is all over h, g of x plus h, g of x. So we need to basically manipulate these things to get back the things that look like definitions of derivatives in themselves. So to be able to do that, I'm going to have to be very mindful of what to do with that h. I want that h to ideally be a denominator for that term and also to be a denominator for that term. So I'm going to go back to the blue statement I wrote down earlier, which was a over b over c was the same thing as a over bc. So before, when I wrote this down last time, we went from a statement which was basically like this to a statement which was a bit more like double star. Now I have something which is looking a lot more like double star here. And this is my A, this is my B, and these things here together I'm looking at as my C. So what I'm now going to do is actually go the other way to be able to go the other way to get a statement which looks a little bit more like this. Okay, so for the purposes of sort of space, I'll just get rid of this and I'll start doing what I've just said. So what we actually end up with is we have this limit thing here, but then we have f of x plus h minus f of x, and of course the g of x is there. And what I want to do is, before I do anything, I want to take that minus out. So all of this is going to be over h, and then all of that is going to be over g of x plus h times by g of x. Right. So when we have that, we need to tidy this up slightly further. I can basically take that h and split that top fraction up into two separate fractions, one fraction there and one fraction there. So I've got the limit as h tends to 0 of f of x plus h, take away f of x times by g of x, and this is over h, and then I've got minus f of x times by g of x plus h, take away g of x, and all of this is over h. And of course the denominator for the whole thing is still there. So now at this stage we're actually nearly done, because this thing here is obviously going to give us our derivative for f. This thing here is going to give us our derivative for g, and this thing here is going to give us our g squared. Okay? And as I take the limit, those h's are going to be eaten up by the limit effectively, because they're going to work together to give me the derivative of f, and these are going to work together to give me the derivative of g, as I've already said. Given that at this stage there's only a g there, the limit is in terms of h, so the limit's going to leave that g alone entirely. So likewise, there's only a f here in terms of x, not in terms of h. That limit is only going to see this term here on the right. So once I've done both of that, the numerator, I should write this in black, the numerator, in line with the red statements above, is actually going to give me f prime of x g of x minus, because of the minus we've got here, minus f of x g prime of x. Okay, so that's the numerator for the entire thing. And the denominator is much like the sort of thing we saw last time. Well, what's going to happen to g of x plus h as h gets closer and closer to 0? Well, g of x plus h is just going to give me g of x, okay? But then there's a g of x here, which I get out of after evaluating the limit, and then there's already a g of x there. So the two of them together are being multiplied, so I'm going to get g of x squared effectively in the denominator. So we've effectively been able to work out the formula for the quotient rule in this case. Let's now go and see what this would look like in Leibniz notation. So as we can see, we can convert the entire argument into a sort of very different notation. So if I define my function capital F of x to be y, and of course we define capital F of x to be lowercase f of x over lowercase g of x, then I've got to define the lowercase f of x and lowercase g of x in terms of different variables. So let's take lowercase f to be u and lowercase g to be v. Then it's pretty clear that if I differentiate capital F with respect to x, that's the same thing as dy by dx in terms of the Leibniz notation. If I differentiate lowercase f of x, that's the same thing as du by dx, and if I differentiate lowercase g of x, that's the same thing as dv by dx. So we basically go to the actual formula for the quotient rule, and for each part of that formula, we replace each sort of derivative or function by its counterpart in terms of v, u, or y. So f prime is going to give me dy by dx. G is, of course, v. Lowercase f prime is du by dx. Lowercase f is just u. Lowercase g prime is dv by dx. And then the function g squared is just the same thing as v squared. So we've actually now got a formula for the derivative of a quotient in Leibniz notation. So let's put a big red box around this because of its importance, and also around the exact same formula in different notation, again because of its importance. So we can now perhaps go and see an example of how to use these formulas very briefly. So like last time, we're going to do two quick examples, one for each sort of notation type. So let's look at the very first function here. Let's do it using the formula as I said. So we define f of x to be x cubed because that's our numerator for capital F, and g of x to be x because that's our denominator. So we've done that because then our f of x, as defined sort of above, can actually be written perfectly in the form f of x over g of x. And I should say, because our denominator for capital F is x, I should not have x equal to 0, otherwise the whole thing breaks down. So once we have that, what is the quotient rule? Well, the quotient rule is g of x, f prime x, take away f of x, g prime x, and then the whole thing is over g of x squared. So we can just substitute things into this formula. So let's see. So our g of x is just x. So I'm just going to write down x. My f of x, my lowercase f of x is x cubed. So my lowercase f prime is just going to be 3x squared. And then my f of x is, again, we already know it's x cubed, so I subtract x cubed, and then my g differentiated is just x differentiated with respect to x, which is just 1. And the whole thing, of course, is over g squared, but g is just x, so it's all over x squared. Now it's just a matter of tidying this up. So the numerator gives me 3x cubed, take away x cubed, and the whole thing is over x squared. But of course, 3x cubed take away x cubed is 2x cubed, and the whole thing is over x squared. So I actually end up with, if I simplify this, I end up with 2x, right? And let's now, as we did last time, let's just differentiate the statement star directly. So let's differentiate this directly. So my f of x, I can simply write down as x squared because I can use laws of indices. And once I've got that, I can just differentiate this as I would normally to get 2x. And it's reassuring to see that we've actually got the exact same answer in both cases. Let's look at the second example. So in this case, we're working in Leibniz notation. So I've got to define my numerator and denominator slightly differently. So let's say u can be the top, which is x squared plus x, and v can be the bottom, which is just actually x. And of course, I've chosen this because then my y takes the form u over v. Right? So once I've got that, I know that the quotient rule in Leibniz notation is actually v du by dx take away u dv by dx over v squared. Let me actually, just for the sake of doing this in a slightly different way, let me use these to write down some things. So if I know u is equal to x squared plus x, then I know that du by dx is actually equal to 2x plus 1. Similarly, if v is actually equal to x, then I know that dv by dx is actually just equal to 1. So once I have this, I can now use the two statements in blue and my definition of u and v to just go to this formula and just start to substitute things in directly. So when we do that, v is just x, so I put that in, I get x. Du by dx, well, that's the first statement in blue that I worked out. That's just 2x plus 1. And then minus u is, well, I know what that is because I defined it. And then dv by dx, well, that's just 1 because it's the second blue statement I've worked out. And then the whole thing is over v squared, but v is just x, so the whole thing is actually over x squared. So now it's just a matter of tidying this up, and that's really no problem, because if I expand the numerator first, I get 2x squared, and then I get plus x, and then I get minus x squared minus x, okay? And this whole thing is actually over x squared. So again, we can simplify this. The x's, of course, are going to cancel. So perhaps I can do that in green. That x is going to cancel with the other x. So once we've got that, I can further simplify this to say, well, the whole thing is just going to give me x squared over x squared, interestingly enough, which actually works out to be 1. So let's see if we can differentiate this directly. So I can write that here. So let me call this sort of double star, and let me do it on the side here. And of course we need to simplify that first. So I can just basically do the division. So I can split that up into say x squared plus x over x. But when I do that, x squared divided by x is just x, and x divided by x is just 1. So now I can basically differentiate each term. And when I differentiate each term, the x differentiates to give me 1. The 1 is a constant, so that differentiates to give me 0. So the derivative is indeed 1. So we see, again, we get the exact same solution for this calculation, doing it both different ways. Again, we will see a lot more examples of using the quotient rule in a much more thorough setting with sort of functions that are a lot more complicated, but we would leave this here for now. So the statement for the chain rule says, if we now define a function capital F by considering a composite function, so a function of a function, you take the function g and you put that as an input to the function f, and that's how you define the function capital F, then the chain rule says, well, if you want to differentiate that, what you want to do is you want to differentiate the function uh, g with respect to x, but then you want to differentiate the function f with respect to g, and then multiply them, and that's going to give you the same answer as the function capital F differentiated with respect to x. This probably looks a bit too complicated to understand. In fact, it is a lot easier when you start to do examples, but for now, let's see a proof. So we're going to just jump straight in to say, well, we know what f prime is defined as. F prime is defined as this limit, obviously, that we've seen many times now. X plus h, take away f of x, and the whole thing is over h. But of course, in this case, we define our capital F in terms of lowercase f and lowercase g. So let's do that. So it's f of g of x plus h, of course, and then take away f of g of x, and the whole thing is over h. And now at this stage, it seems like we're completely stuck, right? But what we actually need is we need a bit of ingenuity, and we can get that ingenuity as follows. So if I write down what we've already got without screwing this up, sort of, right? So I've got f of g of x, and then I've got a h here. So now what I want to do is I basically want to make the argument that if I've got something and if I multiply by 1, I don't actually change anything, right? So let me now write the 1 down in a form which is a lot nicer. So again, I've got f of g of x plus h, take away f of g of x, and this is over h, and now I'm going to write down what my 1 is. The way I'm going to write down my 1 is actually going to be g of x plus h, take away g of x, over g of x plus h, take away g of x. So this is my 1. So once I've now written that down, what I'm going to use is I'm going to use this little algebraic trick, which is AB times by CD is actually the same thing as A over D times by C over B. And that's obviously not hard to understand because when we combine this thing on the left, what we're going to get is we're just going to get AC over BD, but we can swap. You know, multiplication allows us to swap numbers around, so I can say dB, and once I've got it in that form, I can then basically expand this back like this, and I get exactly the sort of statement I wanted. So let me perhaps tidy this up, and so I can just apply that very directly. So what I'm going to now say is I'm going to have the limit as h tends to 0, and I'm going to swap that, and I'm going to leave everything else alone. So I'm going to say f of g of x plus h minus f of g of x over g of x plus h, take away g of x. And then, of course, there's a bracket here, and there's a bracket here, which is g of x plus h, take away g of x, and the whole thing is over h, and that's what we have. And then I have these big brackets. So basically, we're done at this stage, because all I can now do is expand this limit. This limit applies to everything in the brackets equally. So let's expand this. So once we've got this, we're now home because that is the definition of the derivative of g, and that is the definition of the derivative of of the derivative of f of g, but with respect to g, of course. So let's just write that out. So we have f prime of g of x, which is the first thing we've got in our limit, and then the second thing we've got is actually g prime of x. So with that, we've actually worked out the chain rule. Perhaps we need to think a little bit more about why this gives us the derivative of f with respect to g, and we can do that now. So let's think about what f prime of g of x actually means, because this term came up in the chain rule. And for the purpose of time, I've actually written things down so we can sort of run through it quicker. This video is long enough as it is. So in Leibniz notation, if you define y as a function of f as a function of g of x, so it's a composite function, what we actually have is we can take the g of x itself to be a new variable u. Okay, so when we have that, basically y is a function of u. So now when I differentiate f with respect to everything on the inside, but everything on the inside is now called u, so it's the same thing as f differentiated with respect to u. Okay, so f prime of g of x is the same thing as f prime of u, which is the same thing as dy by du. Now, what does that mean? That just means that dy by du basically measures how y changes as you start to change u. In other words, f prime of g of x measures how f changes as you start to change g. So let's go to a graph potentially. So we've got the y-axis and we've got the u-axis. So in other words, because u is g of x, we've got the output of the function g running on the horizontal axis here. And this graph is telling us how y is going to change, or how y behaves as g starts to change or u starts to change. Okay, so if I now go to just 2 points on the curve of this graph, and then do the exact same argument as I've done in the past, when we define the derivative, we find that because u, or g more particularly, is actually a function in itself, well, you can change the value of x to be able to change the value of u. So when I go from one value of u to another value of u, the way I'm going to do that is by changing one value of x for another value of x. And the minute you've got that, you know what the value of the function is going to be, because you're just going to put in this input value into the function to get this output value. And similarly, we're going to put this input value into the same function to get this output value. So once we've now got a set of input and output and another set of input and output, we can basically do the change in y, and we can do the change in x, and we can write out a fraction change in y over change in x. And once we write that down, we get exactly the sort of thing we got in the calculation for the derivative of a chain rule. And when we take the limit of this, the thing we get is f prime of g of x. So I hope this goes to explain why the chain rule is actually working. So chain rule is probably a lot more easier to use in Leibniz notation, and you can sort of see why it's called a chain rule more visually in Leibniz notation. So let's convert what we've got from Newton's notation to Leibniz notation. So let me define y equals f of x as my function, the capital F of x, and also let me define my u as g of x. Okay. So once we have that, since my capital F of x can actually be written as f of g of x, then what I actually have, this is the same thing as y is equal to f of u, right? But let's now start to convert this. So what happens if I differentiate capital F with respect to x? Well, that's just the same thing as y differentiated with respect to x. And what happens if I differentiate my g with respect to x, because g is a function of x? Well, that's just the same thing as u differentiated with respect to x. And likewise, what I do need to know, which I can sort of see directly from this term here, is I need to be able to differentiate my f with respect to g. So let's write that down. So I've got f with respect to g is here, but then that can be written as f. Perhaps I should do it slightly better. That can be written as f with respect to u. So when I now differentiate f with respect to u, that's basically the same thing as f differentiated with respect to with respect to g of x. So now that we actually have all of this, let's convert the statement for the chain rule from here to an equivalent form in sort of Leibniz notation. So the left hand side is actually f prime capital F prime, which is obviously dy by dx because we have that here. And then we have the far right is actually g prime. And then we know what g prime is. G prime is just du by dx. So I'm just going to write down multiplied by du by dx. So the only thing we actually need is we need f prime of g of x, which I actually have here. But this is not quite written in the full Leibniz form yet. What I can do is I can sort of be a bit more careful about this, right? So that statement should help us figure out what this statement here would actually give us. So think about this. I've got f prime of u. Well, what is f prime of u? Well, that's just this star statement differentiated, yes? And indeed, this part is differentiated with respect to u here. So so when I write this in Leibniz notation, I'm going to get dy by du, right? So I can now go back and I can actually put this into into the part that I actually want it to for this sort of thing here. And now we actually have the chain rule description in Leibniz notation. And you can see why it's called a chain rule because it makes a chain. The u here is linking with the u here in some way, right? So you've got a chain of y from y to x, and it goes from y to x via u. So it goes from y to u, and then it goes from u to x. So you end up with going from y to x, and that's the chain rule. So let's apply that to do this example. So let me just say y equals sine of x squared, and let me say let u equals x squared. So I actually end up with that tells me y is really just the sine of u. So using the chain rule, I want to go from y to x, but I can go from y to u, and then I can go from u to x. So how do I go from y to u? I just go to y as a function of u and I differentiate it to get dy by du. So what do we get when we differentiate a sine? Well, we get a cosine, and we showed that in the previous video. So that's straightforward enough. And then for the second part of this, we've got to differentiate u with respect to x. Well, I've got u as a function of x here. Okay, so when I differentiate u as a function of x, I'm just going to get 2x. And now this is my answer. My answer is 2x cos of u, but we don't want to leave it in terms of u because we want to write everything in terms of x. So we can write down 2x cos of replacing u by x squared because that's what u is defined as. So we've been able to work out the derivative of something a lot more complicated, which is a sine function, with the argument itself being a non-trivial function. So we are going to look at lots and lots of more examples on this. So don't worry if you found this a little bit challenging. I would finally like to say thank you for watching. Do hit the like and subscribe buttons if you found this useful. Uh, do leave a comment in the comment section to let us know what you would like to see more videos on, and we will see you in the next video.